Now, where would we be without metallic bonds? So metallic bonds, and we're talking about like a chunk of iron, so think of a nail or aluminum pop can or a tool. The bonding between those individual atoms is not covalent. So instead, what holds these molecules together is bonding that results from the attractions between the nuclei and the delocalized electrons that move throughout the entire structure, what we call the sea of electrons. I'll show you a picture of that a little bit later. Bonding strength, so that what holds those together, increases as the number of bonding electrons increases. So you think of sodium, which only has one electron on the outside, 97.5 degrees Celsius. Iron, which has 8, is going to have a melting point of 1,538. So yeah, pretty significant difference. So what we mean by delocalized electrons is what happens is we set up a repeating pattern of protons, nucleus, and the electrons that are on the outside, the valence electrons, don't actually just stay with one particular proton. They're moving all around, and so they're kind of swarming. So this electron might be with that proton, then it's going to move over to that proton, and maybe it'll wind up here or over there. Since they're moving around like that, we call it a sea of electrons. So imagine those electrons just kind of flowing around wherever they want to go. And the nucleuses actually do not move. They stay in a particular place. That's why metals are extremely rigid, but they do bend fairly easily because we can delocalize, we can move around those bonds. So they're not locked into place. What's holding them together is just those free-moving electrons. Also, as a result, then, metals conduct electricity, they conduct heat, they're malleable and ductile. Malleable means they bend, ductile means we can stretch them into wires, and they lack directional bonds, so there's nothing really to lock them into one particular place. What makes them conduct electricity? Electricity is the flow of electrons. And look at this, these electrons are already flowing. So if we take a voltaic cell and we put it on that side, it's going to act to push the electrons one particular direction. So as a result, if we have a wire hooked up to a battery on one side and a light bulb on the other, the battery is going to push those delocalized electrons through there like a wave going through the ocean and cause that bulb to light up. Now this only happens with valence electrons, so you're still going to have the core electrons that are moving around in those SPD, whatever you want to call them. It's just the valence electrons that are on the outside that are going to be sliding all around each other. And what's cool about this is we can actually mix metals together fairly easily. It's called alloys, so if you think of brass and bronze and things like that, they are mixtures of things like copper and zinc. And so what you do is you might have several coppers mixed in here, and then you just throw some zincs in there as well. And since they all just bond with delocalized electrons, it's really easy to get them to mix together. As a result, though, of the different compounds in there, the different atoms in there, you get different properties. So brass does not behave like either copper or zinc. It behaves like brass. And so throughout history, different metals that we come up with, so the Bronze Age, have been formed because they discovered, hey, if I mix this rock with this rock, I get some pretty cool armor and weapons. Let's start doing that and take over another village. We've moved up from that, though, and we've started to do things like titanium alloys that have really, really strong strength and don't rust, or stainless steel, another great shiny metal used in a lot of kitchenware.